Imagine waking up tomorrow and realizing you're no longer in control of your own body. Your legs move, but you didn't tell them to. Your arms reach out, but the command didn't come from your brain. Something else is driving now, something ancient, something patient, something that has been perfecting this nightmare for over 48 million years. Deep in the rainforests of Thailand, a carpenter ant named by scientists as Camponotus leonardi is going about its morning routine. It's collecting food, communicating with its colony, doing what ants do. But something is wrong. Yesterday, a single microscopic spore landed on its exoskeleton. A spore so small, so insignificant, that the ant never noticed. That was its death sentence. Within 24 hours, that spore will burrow through the ant's armor. Within days, it will spread through the ant's body like a network of living wires. And within 2 weeks, this ant will climb to a specific height, bite down on a leaf with supernatural precision, and wait to die as a fungal stalk erupts from its skull. This is Cordyceps, the zombie fungus. And what it does to its victims makes every horror movie you've ever seen look like a children's story. Cordyceps is not a single organism, but a vast group of fungi with hundreds of species, found across much of the world. Each species has evolved to infect a very specific host. One of the most studied, and most disturbing, is Cordyceps unilateralis, a fungus that targets ants. The infection begins almost invisibly. A microscopic spore, far thinner than a human hair, drifts through the humid jungle air. It doesn't need to be eaten. It doesn't need an open wound. All it has to do is land on the ant's exoskeleton. Once attached, the spore activates. It releases specialized enzymes that slowly break down the ant's protective shell at a precise point, creating a microscopic entryway into the body. The process is so localized and subtle that the ant's immune system barely reacts. The ant keeps moving. It keeps working. It has no idea the infection has already begun. Inside the body, the spore transforms. It grows into thin, branching fungal threads called hyphae, which spread through the ant's internal cavity and form an expanding network. At this stage, the fungus is careful. It does not kill the ant. It avoids critical organs. It keeps its host alive. The hyphae weave between muscle fibers and internal tissues, slowly tapping into the ant's metabolism and redirecting nutrients toward fungal growth. Over the course of several days, the fungal network expands rapidly. Studies suggest that a significant portion of the ant's body mass can already be fungal tissue, even though the ant still appears outwardly normal. The host continues its daily routine, but inside, a foreign biological system is taking shape, quiet, precise, and ancient. And the fungus is preparing for the next phase. As the infection progresses, subtle changes begin to appear in the ant's behavior. The ant becomes disoriented. It stops following pheromone trails. It drifts away from the colony. Other ants often sense that something is wrong. Infected individuals may be attacked or removed before the fungus can complete its life cycle, evidence of an evolutionary defense that has developed over millions of years. But if the infected ant escapes detection, the fungus advances. At a specific point in the day, often near solar noon, the ant abruptly changes course. It turns away from the colony and begins to climb vegetation. The ant ascends to a narrow vertical range above the forest floor, a zone with stable temperature and extremely high humidity. These conditions are ideal for fungal growth and spore development. How does a fungus with no brain, no eyes, and no nervous system achieve this? Research suggests that Cordyceps does not directly take over the ant's brain. Instead, the fungus forms dense networks throughout the body, particularly around muscles and neural connections, altering how signals are translated into movement. The brain itself remains largely intact. The ant is still alive, still responsive. But its body no longer behaves the way it should. The result is a living organism whose movements are subtly redirected, not through conscious control, but through biological interference at the cellular level. The ant is no longer fully in charge of itself. Once the ant reaches the optimal location, the fungus triggers its final behavioral command. The ant's mandibles clamp down onto a leaf vein with extraordinary force. This behavior, known as the death grip, locks the ant in place permanently. Fungal tissue infiltrates the jaw muscles, causing them to contract and remain fixed, even after death. The ant will never release. Over the following days, the fungus consumes the remaining internal tissues. Muscles, fat reserves, and organs are gradually broken down and absorbed. What remains is a hollow exoskeleton, a protective shell surrounding a growing fungal structure. From the back of the ant's head, a single stalk begins to emerge. This structure, called a stroma, pushes through the exoskeleton and grows upward toward the light. At its tip, a bulbous reproductive structure forms. Inside it, millions of spores develop, each one capable of repeating the entire process. When mature, the structure releases its spores into the air below, covering the forest floor beneath the ant. Any ant passing through this invisible zone risks becoming the next host. Ants and cordyceps have been locked in an evolutionary struggle for tens of millions of years. Evidence of this relationship appears in fossilized leaves bearing the distinctive marks of infected ants, dating back to the Eocene epoch. Over time, ants have evolved defenses. Colonies identify infected individuals and remove them. Some species employ specialized workers to dispose of contaminated bodies. Others avoid areas where outbreaks are common, effectively creating natural quarantine zones. But the fungus adapts just as quickly. Each species of cordyceps is finely tuned to a specific host. A fungus adapted to one ant species cannot infect another. Some release spores at night. Others shorten the infection cycle. Certain species even manipulate where on a leaf the ant bites, protecting the fungal stalk from rain. Every adaptation is met with a counter-adaptation. This is not a battle that ends. It is a system that keeps evolving. Popular culture often imagines cordyceps jumping from insects to humans. In reality, this scenario is extremely unlikely. Cordyceps species are highly specialized. The enzymes that penetrate an ant's exoskeleton do not work on human skin. The mechanisms that alter insect behavior are incompatible with the human nervous system. However, the broader lesson is more unsettling. Climate change is pushing fungi to adapt to higher temperatures. In recent decades, new fungal pathogens capable of infecting humans have emerged, and nature has already demonstrated that parasites can influence behavior. Toxoplasma gondii, a microscopic parasite found in a large portion of the human population, has been linked to subtle behavioral and neurological changes. Cordyceps itself is not the threat, but it proves something important. A mindless organism can evolve to manipulate complex behavior. Right now, in forests around the world, ants are being consumed from the inside. They climb, they bite, they die. Their bodies remain, but control has already been taken. Cordyceps does not feel fear. It does not understand suffering. It simply follows a process refined over millions of years. In the microscopic world, there are no villains, no mercy, only survival. And Cordyceps is just the beginning.